if A, or better, let's say LA and LB are, or let A and B be Turing recognizable languages. By this, we mean they are phrase structured languages. Phrase structure languages. Then is the union of two of them is LC phrase structure language, meaning it's Turing recognizable? So the answer is yes, because we can draw or we can create a machine that is able to accept both languages. And you can see it as having two different machines, like maybe you can think even of a selector of a machine. Maybe you have machine A and you have machine B, and each one of them has its halt state or accept state, and then you can process them in parallel. This is you can use a very useful theorem, which is, let me go there to tell you exactly what number of this theorem is. It has to do with the multiple tape Turing machine. It's theorem 3.1. 3.1, meaning that for a multiple tape M, there is a very ugly letter. There is a traditional M Turing machine that, such as the language of the multi-tape machine is equal to this new machine. So let me explain this on a new page, and we will go back to this, okay? So you can regard a multiple tape Turing machine as something like this. Imagine you have a tape here and you have a head that is reading each one of the cells, and also the tape can move left or right, okay? So we have a set of symbols here, and also as we want to have multiple tapes, we can draw here another tape, and of course the head will be in a different position. So maybe you can think of something written here, X, Y, X, Y, Y, X, or Y, Y, X, Y, X, X, etc. So this is a machine that is connected, it's at a certain state, a certain point, and it's connected with two heads, each one of these heads reading a different part of different tapes. So I will erase this part of the machine because, well, just because it's messy, the drawing will get messy. So you can imagine this for two different tapes, but also you can imagine this for any number of tapes. So I will continue for two tapes, but the concept can be extended for any number of tapes. So if you align them, if you see these two tapes as a single one, we can see something like a glue here. And then we can see that we can write both symbols at the same time, something like this. So now it's glued, and of course we cannot, if it's a single tape, we cannot have two different heads at the same time. So we will align them according to the current position. So if we align them, they should go as this: X, X, Y, X, Y, Y, X, etc. So our original head was here, and the other head is here. So we will align that X here, X, and I don't know, Y here, and other things. We don't know what is there. And to the left part, we have Y, X, and of course we extend this not to lose any information. So here we will have empty cells. Okay, now we have our single tape and it's aligned. And now we can use a single head. So what will happen now if we want to move them independently? Well, we need to rewrite all symbols. Supposing we want to change this tape and move to the right, then you can imagine that shifting to this position here would imply moving everything to the right. Then in our drawing of a single tape, it will be something like this. Then now I need to align this Y here to the current position of the tape. Then I have Y, X, X, Y, and everything that was to the left of the Y, X, X, Y, Y. So now you can see we have aligned this Y with the original X that it was here and the previous X was here. So what I'm doing is moving the second tape, but now this is a single tape. So you can imagine this. I think it's better if I don't draw the division part or the divisory line. That we have symbols like this that are composed symbols. So I'm changing this part because I want to simulate I am moving the lower tape. If I move this lower tape to the right, then what I'm doing is kind of a shift right, but without deleting anything. So I will create a machine that goes to the leftmost part and then move to the right. So here we will have an empty space to make it clearer. So we will have here an empty space. Why? Because, oh, sorry. Because I am inserting here a blank space because I want to move the lower part to the right so that X and Y are now aligned. Why I'm doing this? Because I want just to move the lower part of the tape to the right. So a way to simulate this, because I cannot move two tapes at the same time, then I will just rewrite all symbols from the lower part of the tape until I find a blank symbol, because if I do it infinitely, then I will never finish, right? But remember that all strings I will accept are finite. Okay, so you can think of a machine that does this, right? You can think of a machine that just shifts to the left, inserts a blank space here, and shifts to the left all symbols to the right. So this is not difficult to conceive. We have just seen a similar machine, which is like shift left, shift right. So now I am inserting here a blank space and moving all the symbols to the right. The top part left remains unchanged. Yes? So far, are you following me? No problem. Okay, so where am I going to? I am showing that then with this mechanism, I can simulate two separate tapes into a single tape. I am simulating the movement of a tape, which in this case is the lower tape, but it can be also the upper part of the tape. And now I have glued them into a single tape. Now there is a last problem remaining, that is, okay, but then what kind of symbols am I using? Because in each cell, we need to handle only a single symbol, and I am putting two symbols inside the cell. Well, don't worry, we can consider all possible combinations of symbols as a composed or a composite symbol. So we can imagine, for example, if we open here a small window, what we can have the following combinations of symbols. We can have X, we can have XX, or X empty. We can have also Y and Y empty, and we can have YX. And finally, we can have empty on the upper part and Y on the lower part. So if we consider these as composite symbols, then we can maybe create or call this symbol alpha, beta, gamma, delta, eta, and phi. Well, it was not phi, but I forgot the name of the following Greek letter. But if you think of all, then you will be able to represent this as a single symbol: alpha, beta, gamma, delta, eta, and phi. And thus, instead of writing all of this, for example, think we want to represent this in our new symbol names. Well, you just go and say, okay, then we have, and I forgot blank blank. So maybe blank blank will be, I don't know. What, which one?
YY.
YY, or YY, yeah, of course. Sorry for that. So we need more Greek letters. Blank blank will be, I don't know, C, and white Y will be, I don't know, which one do you like?
Looks like we are running out of Greek letters.
Not there. Greek letters here, because I don't know them properly, but if not, then we go to Cyrillic, and then we have a lot of more letters. Okay, so if we have blank
and Y down.
Which one? Sorry.
X up and Y down.
Yeah, sorry for that. X, Y, and Y down. So here this will be
Lambda.
Lambda. It's kind of confusing because we have used lambda for other things. Yeah, we could use lambda, but I don't know, better sigma, let's say sigma. So if we have blank blank, our code says it's C, then blank Y would be phi, and blank Y again phi, XX is beta, and YX is delta, XY is sigma, YX delta, YX again delta, and blank Y is phi again, and here we can say it's blank blank, all of them, so it will be C, 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 etc. It's like a half C, half Z, sorry. Well, what I want to illustrate is that we have converted all possible combinations of symbols into a single symbol. And of course, we can go on this process if we can even more than 2, 3, 4, etc. cells. Then we can have another, or we can modify our machines that are multiple tapes into a normal, usual Turing machine with a single tape. And because this mechanism, well, I have just explained it like very roughly, but with this mechanism, then we can assure that there's always an equivalent Turing machine for a multiple tape Turing machine. Why is this useful? Well, because we can think that that we can combine different Turing machines, each one operating into their own tape, and then we can think of a combination of, well, it's not straightforward because we also need to combine this into the way of the algorithm working, but this allows us to think of 2 different Turing machines that will be operating in different tapes. So if we have this and this operating at the same point, at any time any of them reaches the halt state, having read completely language A or language B, then we can say we have a phrase structured language. And because we have always this mechanism of combination, then we can say that the union of any 2 languages will be also a phrase structured language, or a true Turing recognizable language. So please, again, do not be confused about decidable language. Remember that decidable is that L is a phrase structured language, and also the complement of it is also a phrase structured language. Then L is decidable. But in this case, when we say Turing recognizable, we just care about the first part, is a phrase structured language. Is the complement a phrase structured language? Well, we don't know, okay? So what will happen if we have the intersection of two languages? So the intersection of any two languages, which it will be here again, LC, then we ask, is LC always, and here always, a phrase structured language? And then we have, we can rewrite the intersection between LA and LB. We can rewrite them as the complement of the union of each one of the complements. So we can rewrite this as LA and union LB. Then, in this case, you will say, well, but then I cannot prove that always the complement of LA exists. How can I say this part? So in this case, it is possible to construct this because we are looking for the complement of this complement. Then we can ensure in this case that yes, meaning that the intersection of any two languages that are phrase structured language is a phrase structured language as well. So this was part of the homework. Thus, we can say that for any pair of languages, the result will be always a phrase structured language, and it's okay. And we can extend this to any number of languages if this is a finite union or finite intersection. The problem comes when we think of infinite unions and infinite intersections, because when we add the part infinite, then we will allow an infinite number of languages that will be constructed, and then we cannot sustain this way of reasoning. So whenever we have two or more or a finite number of languages, finite unions are okay, or finite intersections are okay as well. The problem comes when you find infinite unions and infinite intersections. So I will let you keep doing this research on infinite unions and infinite intersections so that you can find it by yourself. And we will discuss this again next class in case there are more questions regarding this. Okay. Well, I partially answered your question, Christian, but on purpose, I still want you to look for more information. Of course, as I said before, it's very difficult that you come up with a demonstration by yourself, not because you are not smart, but because you need to follow certain steps, and they have taken a lot of time to a lot of people. So it would be too much to ask you to find this just by yourselves. So that's why I ask you to go and find some solutions previously done. I don't know, Christian, if you want to share what you found about trees or things that have to do with the strings or not.
Yes, I'm going to find it, and I'm going to share the link in the chat.
Okay, thank you very much, Christian, so that we can check it. Okay, so the subject of today has to do with universal Turing machines. So we will learn to code a Turing machine, trying to emulate the problem we saw with the Guru machine. You remember the Guru machine? It was
Yes,
like this.
I think yes.
The comes from Gödel, right? And mixing Guru and Gödel. So we want to do something similar. I promised you that this confusion about the Guru machine and the problem that solved Gödel, we would take it to the Turing machine's domain. So that's what we will do today. So first, we need to find a representation. Do you remember that we saw some kind of representation that was 0 equals 0? And this was represented in terms of certain symbols. I don't know if the 0 was indexed as 3, and the equal like 6, and again 3, something like that. Why? Just because we can index 0 as 3, and maybe other operations. Multiplication can be number 5, addition can be number 7, and equals is number 6, etc. You can just map any number to each one of these symbols, and maybe after you have defined all of them except 0, I don't know why 0 is equal to 3, but well, this is just arbitrary equivalence. So you can go further, and after a certain point, you can represent natural numbers as another corresponding natural number. It's just a codification system or a coding system. So when you code numbers like this, then you add a prime number representation. You know, prime numbers start from, I think they start from 3, just to avoid problems with 1 and 2. So 3, 5, 7, and 11, etc. And then we have an exponential form. For example, 3 goes here, 6 goes here, 3 goes here, and then we have 3 cubed multiplied by 5 to the power of 6, and then 7 cubed. And this cube number, because it will be a horrible big number, this will represent, yes.
What about 2? 2 is prime number, right?
Yeah, but I'm not sure if Gödel used it for some reason. But well, it's not. Maybe he used for representing the start or something. I'm not quite sure. But well, we can start from we can start from 5 or 7.
Yeah, of course.
But yeah, of course, 2 is prime number. So we have this, and we have the result here. Maybe if you have a calculator, you can calculate it. It's not so relevant. What I want to show you is that how we are converting this 0 equals 0 into a number. It's just that. And then what he encoded, it was the self-reference to this number, saying that the number corresponding to this assertion and said is false. Saying I am false. We will do the same, but with Turing machines. I think it will be more understandable by using what we already know. For this, we need a coding system very similar to this one, but instead of using powers of prime numbers, we will use a positional encoding system. So first of all, we need to know how to code symbols and states. So following the same coding system that is explained in the brochure, because we can think of a lot of different ways of coding. So let's say we will use an alphabet of X and Y, or 0 and 1 originally. So we can say, okay, whatever was X, whatever was Y, then now it will be X will be represented by 0, 0, 0. And Y will be represented by 4 zeros. And why did I started from 3? Well, because first, before I want to add the symbols for right and the symbols for left. So this is our coding system for symbols. Why do I put them in the same line? Well, because remember that for the resulting operation of a Turing machine, you can move the head to the left, move the head to the right, or we can write an X, or we can write a Y. we can add additionally more symbols. Supposing, for example, we have Z, then we can extend this by adding 5 zeros, etc. So this system is extendable to any number of symbols, of course, finite for the set of sigma. Okay, so let's not consider Z in this case. So we have, sorry. Because I have some interference here. Okay, so please say something so I know that I can hear you.
Hello, hello.
Good, thank you, thank you. Okay, so continuing with this way of codification now, we need to codify any symbol, any state. Now, we have at least 2 different states, the initial state and the halt state. And from them, we can say the initial state will be coded, will be codified as 0, and the halt state will be codified by 0, 0. And if there are more states, let's say the state 1 will be codified as 3 zeros, and as before, this will work for any number of states. Okay, so let's apply this with an exercise. Let's try to codify. I will erase this part of the Guru machine. So we can have, we will try to code this machine. That is very simple. It will just read a blank space or and then write an X, or read an X and then move to the right and then halt. It's a very simple machine because we want just to code it in a simple way. So we have here, if we write the transitions as we have been drawing them, remember we have a transition that says for the first arc, we have the transition goes from state I and reads a blank symbol. I know there is no E. And then goes to state H and writes an X. This is the first transition. Sorry. Oh my God. Sorry, I'm not writing this properly. Sorry. Okay, so given iota, the initial state, and a blank space, then we will go to the halt symbol and then write an H. So this is our transition for the first arc, for this one. For the second one, we will have from the initial state and then given an X, we will go to the halt state and then move to the right. This will be the second arc here. And that's it. So I will give some space here. And then let's start codifying it. The initial state is a 0, and the blank space, I forgot to put here, but blank space is 0, zeros. So nothing. The halt state will be 2 zeros. And finally, the X symbol is represented by 0, 0, 0. And then how can we know where do they start and they end? Well, of course, we have not used the number 1. We are using all zeros. So we will add 1 here, and then 1 here, another 1 here because there are 0 zeros there, and then another 1 here, and finally 1 here. For the second transition, well, we will not add this one. For the second transition, I have 0. The initial state is 1, 0. For the X is 3 zeros. So we have 3 zeros. The halt state is, as before, 2 zeros. And finally, the R is represented by 2 zeros. So we have this. The same as before, we will have the one at the initial at the beginning, 1 to divide this, 1 to divide this, 1 to divide this, and because this is the last transition, we need to add a 1 at the end. And that's it. So we have coded our 2 transitions into this, and what we need to do now is just to write them together. So we have 1 0 1 1 0 0 1 0 0 0 1 0 1 0 0 0 1 0 0 1 0 0 1, and that's it. It's the binary representation of a Turing machine. So please note that there is no 2 ones together here because this has no ending 1. But the whole machine starts always with a 1 and finishes with a 1, right? So this is a valid representation of a Turing machine that you can reconstruct. And also, please, now I ask your help. Can you give me the decimal number of this machine? The equivalent to this one. Maybe you can use Google, because if you use a calculator, it will overflow with numbers.
That's a big number.
Yeah. So you can write the number and maybe find a binary to decimal converter.
One question, teacher. In the,
yes.
The 2 ones, we can represent the delta, or we can join the 2 ones in the final
With
representation.
this one or here?
In the final, it's 1 0 1 1. No,
1 0
in the final
1
string, in the final.
1. Yeah, this 1 0 1 1 0 0 1.
The second one, we write it with a white space between the 2 ones.
No white space, just together. You mean this one?
No, the previous
like
one.
Space. One. This.
Yes.
This. So yeah, you just write 1 1, just like this, and whenever you find a 1 1, then you know it will be a blank space. So this is 0 zeros. You can find 2 ones together. So in this case, you have two ones together. So have you found this number?
Yeah, it's in the chat.
Okay, let's see the chat. Yeah, correct. So we have that number. Thank you very much. So we write this as base 2, and this will be base 10, or the decimal number. So now we have something very interesting, because this is a very nice number. This is machine number 5,837,897. And if we write this as a subscript of a machine, then we know this is a valid machine. Now we have a kind of a philosophical way of seeing this. You know, all natural numbers are theoretically already defined, right? So you can think of number 100,000,003,000 etc. You can think of any natural numbers, and it will be already defined, right? But in theory, all numbers, natural numbers, are previously defined. Then, if you think that most of these natural numbers correspond to a Turing machine, then it means that all Turing machines are already defined in theory. And whenever you draw or write a Turing machine for any purpose, you are just evoking it. You are just calling its manifestation, thinking of what is creation. Are we really creating something new, or this was already created and we are just recalling it? So, well, this is a little bit just a philosophical point of viewing it. If you see, I think it's Matrix Reloaded, there is a chapter where another chapter. There's a section when they go to a place where there are a lot of screens, and they say the supposed God or equivalent says, well, these are all the possibilities, and you just choose which one of them manifests. Well, it's something like this. They already exist. You just choose one and take it down to manifest. Okay, but apart from that philosophical point of view, then we have a nice property here, is that for every machine, for every Turing machine you can think of, it is already defined. It is there is a number that corresponds to it, and this is natural numbers. Immediately comes to us the questions and the answer of then how many Turing machines it is possible to have. Is this a countable or an uncountable number? So please tell me.
Countable, of course.
Right, and why?
Because there is the amount of Turing machines. Well, I wouldn't say amount. The cardinality of a set of Turing machines is the same as cardinality of a set of natural numbers.
Right, we don't have more Turing machines than natural numbers, then this cardinality is limited by the number, or you can explicitly map each one of these machines to a natural number. And we have found this mechanism, right? So we are studying the most powerful theoretical machine for computing. Then we have a limited number. Well, limited, it sounds a little bit contradictory, but we have a countable infinite set of machines, of Turing machines that we can draw, that we can, well, I mean, I say draw because I'm drawing them, but we can construct. It's much, it's better, it's more exact. Okay, so now that we have this way of coding machines, we can ask several things about themselves. Like, for example, are these machines self-terminant, auto-terminant? It means that whenever the own description of the machine is fed to itself, will it finish or not? In this case, it seems yes, but before we need to do some adjustments. We cannot use this machine in order to process this string. Why? Because this machine was designed for using X and Y. But what if we change, instead of X, we change for 0 here, and then if there was a Y, it would be 1. But we will just use binary numbers, 0 and 1. So in this case, we are replacing X by 0 and Y by 1. So here, this one will be 0, this will be 1. And now our machines accept this language, accept the language formed by strings of 0 and 1. And the machine itself has a description based on the 0 and 1. This is when we are doing the loop, right? Because now we are able to feed this machine onto itself, and then we can ask for some properties. Some of these properties are will this machine stop when this string is fed to itself? And let's see what happens. If we start feeding this one, then we start looking, okay, we have a 1 here, and then we don't have any option for delta or 0. So do you remember what we said in the case for these machines when we haven't the option?
We go to halt.
Yeah, we go to halt. So there is an implicit here, an implicit arc that says, okay, with 1, and we had the movement to the right, okay? Oh, no, we said we just leave untouched, like this. So the original machine doesn't say what to do with 1, but we say we read a 1, leave untouched, or write again a 1, and then halt. Then if we have something like this, the machine will read this one and then halt. Then the question was, will this machine auto-terminate? Will this machine auto-terminate? Meaning that when its own description is fed to itself, it will it will just halt. Yes, but this is not the same. Remember that it's not the same to halt, to reach a halt state, than to accept the whole the whole string, because we have just traveled up to here and then we halted. Then in order to accept this string, we need to follow the whole string. So the second question, well, this is yes. The second question, will this machine accept its own description? And the answer is no. Why? Because this machine just stops here and will not continue reading the rest of its description. So these two things will be very important in order to understand what happens with self-termination or auto-termination. Auto-termination sounds like it will kill itself, right? But I don't know if it says the same in English. Auto-terminant, I don't know. Let me see what is what they say. Give me a second. Self-terminating, says the book. Well, for me, it sounds a bit funny in English. So it will self-terminate? Yes. It will auto-explode itself, right? But well, by termination, it just means halting. In this case, just halt. Well, let's not think so destructively, or like a Robocop or Terminator. Oh, maybe I see so much sci-fi, sorry. Okay, so now let's see another example of a machine that will say yes to both questions. So let's draw a machine that goes whatever it sees. It sees an X, no X, now it will see a 0 and move to the right, and it will see a 1 and move to the right, and it will halt when it sees a blank space. So let's code this machine. Now we know how to code it. Now we will have a greater or a larger number because we are using 3 transitions, and each of them will represent a binary number. So first we have this arc. So we go from the initial state, read a blank space, and then this will take us to the tuple halt and move to the right. So this will be transition number 1. Transition number 2 will say, transition number 2 goes from initial state, reads 0, and then takes us to the halt state and moves to the right. And the final one, number 3, is from initial state and reads a number 1 and takes us to the halt state and move to the right. So these are the 3 transitions defining our machine. Yes, Abraham?
I think that the 2 and 3 return to stage 2.
Oh, yes. Sorry. Thank you, Abraham. So this is the kind of things one does in order to see if you are paying attention. And yeah, I see you are paying. Thank you, Abraham. And yeah, so they return to the initial state. Okay, corrected. Thank you very much. Well, also there's another thing I want you to see, and it's the ordering of these rules, because there is an ordering. So we will proceed always in order of origin of the state. So remember that in our codification system, always we begin by the initial state, and then later we go to the halt state. We shouldn't have output arcs because they will be just ignored, and then we will go through the rest of states. The second criterion for ordering is the symbol. So also you can see that I will use first the blank space and then 0 and then 1. why it's important, this ordering, because this will affect the resulting number, and we want a unique number corresponding to any Turing machine. So this is why the ordering is important, because if we start with this, then this, and this will have a different number. You see? Okay, now we are able to code them. So we said the same as before, initial state is 0, blank space is no zeros, halt is 2 zeros, and R is represented by 2 zeros, if I'm not wrong. For the second one, again, 0, and the 0 is represented by two zeros. Let me go back and check, I'm not sure. 3 zeros. We changed this as well, right? So now this is 0, 3 zeros, and 1, 4 zeros. Okay, go back. And then, so this is 3 zeros. Initial state is 1 0, and right is 2 zeros. Let me check. Right, yeah, right is 2 zeros. Okay, sorry for changing too much. And for the last one, we have initial state. 1 is represented by four zeros, and initial state 1, and right is 2 zeros. So if I'm wrong, you will correct me. Thank you. So we begin. The beginning is marked with a 1, and then we will have 0 zeros, so just 1 1, and we have a 1 here, and that's it. For the second one, we will have a 1 because it's the beginning of a transition. Always the beginning of a transition has a 1, and there's a 1 here, 1 here, 1 here, and that's it. And for the last one, the same. 1 here, 1 1 1, and just because this is the last transition, I will add a 1 here. That's it. So we can write the whole number of our machine. So we just concatenate all the 3 numbers. So we have 1 0 1 1 0 0 1 0 0 1 0 1 0 0 0 1 0 1 0 0 1 0 1 0 0 0 0 1 0 1 0 0 1. Okay, so a very large number, right? So maybe you can try to convert it as well. I don't know if the web page will tolerate such a large number, so let's try it. Okay, I have a number. I know if in order to see if I'm right, I will just wait for you to put your number. I'm using a website called rapidtables.com, but maybe you can use, yeah. Okay, then there are 2 options. One, I'm right, or everyone is not correct, but the more people write it, I think it's more, we can believe we are all right. So it's the truth of the masses. So we have this number corresponding to this machine. Thank you to all of you.
We have a problem.
The truth of the masses. Yes. But well, at least there is a method here, and we can believe that most of us are doing in good faith that we are just writing the same number. Good. So this is base 2, and this is base 10. So this is our beautiful machine. I don't know. I need to count in millions and billions. 5 billion 983 million 343,657. So this is this machine. So it's fun. You see, you can calculate the number for almost any machine, and you will see that there is always this number. So now let's pose the same two questions as before. One, is this a self-terminating machine, Turing machine? So let's see. We feed this its own description to the machine, and then we see, okay, 1 move to the right, 0 move to the right, 1 move to the right, etc. So we keep going, and when it finishes, then we say, okay, no more numbers. We have a blank space. Then halt. Oh yes, it will be self-terminating. And the second question: does this machine accept its own description? Accept its own description? And the answer is, as you probably have guessed, yes. Why? Because we are moving all the way through the end of this machine, and then we halt. It means it accepts this string among many others. Actually, this machine will accept any combinations of zeros and one, right? So, but at least for its description, yes. And then it means that this, if we create or we want to say this with the language, we can say this machine 598334356 belongs to the language of machine 598334356. So I just want you to pay attention to this notation, because I am saying here, I am representing this machine as a string. So whenever I write this, maybe I mean the string of zeros and one. I mean this particular string represented by this M with this sub number. Then it belongs to the language accepted by this machine. It is not equal, because if it was equal, then it means it only accepts this string and no other string. So as an exercise for the reader, can we create a machine that accepts only its own description? So you will think about this next time you are commuting from your bedroom to the dining room. Okay, because there is no other commute, right? Okay, so now we want an example of a machine for which two questions will be no, a machine that is not self-terminating. Okay, so far we are doing well, right? Or so well we are doing far. Okay,
No,
let's, yes, sorry?
no, nothing.
Okay. Okay, so how about a machine that looks like this? This is the initial state, and there is a halt state, and let's say this goes permanently to the right, and this goes to the right, and you see where am I going to, right? So this is a machine that never halts. Whatever it comes, never halts. So now we can try to code this machine as well. We will have three. I think it's time for you to do it on your notebooks, so that I don't get you bored by doing it on the whiteboard. So please codify this machine, and I want you to give me the number. So what is the number of this machine? Okay, so we have an answer. So let's see the truth of majority. Okay, now we have some discrepancy. Let's see how it converges. Okay, so it seems we have a large number. So let's do it quickly in order to see if we are right or not. Let's see, the order should be, this should be number 1, this is number 2, and this is number 3. And for number 1, we have from initial state and blank symbol, we go to the initial state and move to the right. The second one goes from initial state with a 0 and go to the initial state, moving to the right. And the third one goes from initial state with a 1 and we stay at the initial state, moving to the right. This would be with 0, and then no spaces, and then 0 and 0, 0, 0, 0, 0, 0, 0, 0, 0. And R is, I forgot, 2 zeros. And final one is 0, 0, 0, 0, 0, 0, and 2 zeros. Then we put the ones, should be something like this. And the final one has an ending 1. So let's see. Let's try to convert this. And it says 3 million and something.
Teacher,
Yes,
I have a question.
yes, please.
Does mirror the order that I codify this?
Yes, a lot, because it will yield a different machine. We said that the correct order was first from the state of origin. Now we have only one state of origin, so there's no problem with this. But we could have more states. So first we consider this one, and then we consider the states as we codified them. And the second criterion is the symbol. In this case is blank, then 0, and then 1. So this is very important because it will yield different machines. In this case, we consider first blank, then 0, and then 1. And that's why this is the number corresponding to this machine.
Okay,
So maybe we
so
change the order, we have different result.
yeah, I guess that I do this.
Yeah, so maybe it was you had a different number, right?
Yes.
Okay, so now we can answer the following question. Is this machine self-terminating? Now you can give me the answer. Okay, Oksana says no, and she is right. And does this machine accept its own description? So the answer is no. Why? Because it will never stop. So now we have seen different possibilities of these machines, and particularly we will be interested in this part of the machine accepting its own description or not, because it will define a language. So now let's suppose we create a language. Let me change the page. Let's suppose we create a language which we will call L0. So L0 is equal to to a machine, certain machine W, such as this machine does not accept its description. Let's write the description as W. I think it's better. So this is the number of the machine, and this is the machine that does not accept its own description. So you will say, well, yeah, we can do that. We have just done that, right? In the previous example, we saw this machine, and we know this machine, this particular machine, 3 million, let's call this machine 3 million and something, 3 and comma, just because it's a billion, or if you like 3 billion, 3B. Okay, so when we ask this, then we say, yeah, why not? We know that machine 3 billion, or the number 3 billion, belongs to L0, because this is an example of machine that does not accept its own description. We know there are machines such as this one, right? Okay, now here it comes, the loop to itself. Now we can ask, is this language L0 computable, meaning that there should be a machine that accepts or not, that is able to accept this language. So in order to do so, then we need to see the following. If there is a machine that accepts L0, and this machine, it's called the language that accepts this machine. If there is a machine that accepts this, then we can call this machine as W0, because it has a number associated to it, right? So again, there is this language, and we want a machine for doing so. This machine will be called that machine W0. There should be a number associated to this machine. And then we can ask, is this machine accepts itself or not? And then here we have the contradiction, because if we ask if W0 belongs to L0, then it means that it accepts it, but it shouldn't. Then we are contradicting this. Then we say, okay, then it doesn't belong to L0. Then it means that it should belong, because L0 is composed precisely by those that accept it.
Are you
Sorry
writing?
to interrupt you, Doctor, because we don't see your notes.
Oh my God, too bad. Yeah, I was writing a lot. So let's start it again. Why in this moment? the infinite refuses to be analyzed by us. Okay, so I didn't write too much, just that, but again, I will explain again. Okay, so begin from zero, begin from L0. We have this language, and this language will be composed of all those strings, such as there is a machine that belongs, that corresponds to that string, so that it doesn't accept W. So this is string. An example of this machine is just the previous one. We have seen the machine 3B here, and the machine 3B, who is that? Well, is this one. This is machine 3B. Why do we call it 3B? Well, just because of its description, which is 3 billions and something, billions in American billions. If you use English billions, then no, or billions in Spanish, no, but it's American billions. So this is machine 3 billions. So we have just proved, or we have examined this machine, and we know that this machine does not accept its own description. Why? Because it will never, it never halts. So this is an example of machine that does not accept its own description. So now we want to have all the collection. We want to form a language by a language that is formed by all the collection of these kind of machines. We don't want just machine 3B. We want all of them. We want a recognition. Yeah.
So L0, L0, I think, is all natural numbers for which exists a machine corresponding to this number. And this machine should not accept this number.
Correct.
Okay.
Yes, yes. Okay, so but we are going there. Not yet. Well, we have went there, but we went back so far. But we are going exactly there. So far, we have this machine, machine 3B. Machine is exactly this machine, and this machine does not accept its own description. Then we want more machines like this. How many machines that do not accept their own description are there? Can we count them? And maybe we are not so interested in counting them. Maybe their number is infinite. It should be countable, but maybe it's infinite. So more than how many we want to recognize them. In order to recognize them, we create a language. This language is called L0. So we say, let's create a language L0 such that is formed by all those numbers for which its machine does not accept its own description. So we have seen the machine 3B, this number in binary, belongs to L0. We know that because we have seen that before. Okay, so let's see, can we define this language or not? Because if we define it, then there should be a machine called W0 such that this machine accepts exactly language L0. L0 is the language of this machine. Yes, this is just notation. We have this machine. Every machine has a language associated to it, and we want this language for this machine to be L0. Because we have learned how to codify machines, then we suppose we are able to codify this machine in certain numbers. So we need to find this number W0, but because it's very complex.
But we are not sure that this machine even exists.
Yeah, we are going to that. So let's suppose we can find this number W0. It's so complicated, so just let's call this abstractly number W0. We assume maybe it's a very large number. So because we are able to define a machine such as this, then we can ask ourselves, is this number W0 belong to L0 or not? Then here we are in trouble, because if we say W0 it's here, then there is a machine that does not accept W. However, in order for it to belong to L0, it should belong So if it belongs, then it shouldn't belong because of the definition. Okay, let's say the contrary. W0 does not belong to L0 because the previous one was contradicting. Okay, so we say it doesn't belong. But if it doesn't belong, then it should belong. Because precisely if it doesn't belong, then it's one of those machine or description that does not accept W. Then again, contradiction. And because we have contradiction in two ways, then we say W0, we cannot determine W0, 0. We cannot determine or find W0. Therefore, there's no such machine. Therefore, we cannot compute L0. And therefore, L0 does not belong to the phrase structured languages, or L0 cannot be accepted by any Turing machine. So you see, this is the limit of computation. There is a language that it's defined in terms of all the constructing blocks that cannot be computed. This is exactly the same problem that observed Gödel when he defined something that in terms of Principia Mathematica was able to define, and definition is properly done. However, it cannot be proved. So this is the limit of computation. Yes?
But what exactly is the problem? Like we established that this set of numbers is not a language, well, not phrase structured this language. So what's the problem with this?
The problem is that you cannot build a Turing machine that recognizes or that tells you if any string, for all strings, they belong or not to L0. It cannot tell you when they belong.
So that's like an example of to show that Turing machines are not all powered.
Yes, exactly. That's the point. And precisely this is the limit of Turing machines. However, there are more languages than Turing machines can accept. Let me change my projection into this one that we have been seeing several times here. And this is it. So we are here. Let me, oh my God, where is my pencil? Markup. Yeah. So L0 is here. L0 is a language because we are able to define it. However, it's not a phrase structured language because it cannot be processed by a Turing machine. Actually, so far, we don't know a way for being able to process it. So L0 is non-computable. And let's see how it looks in terms of a Turing machine. Let's suppose I go back to my whiteboard.
So in this sense, we can prove that a problem is uncomputable, or I don't know how you say this, trying to construct a Turing machine.
Yes, we cannot build a Turing machine that accepts L0.
Okay.
That is the question, right?
No, we can prove that a problem, or I don't know, how do you say? It's hard, it's uncomputable. We prove this trying to construct a Turing machine if the Turing machine, I don't know, how do you say, don't accept this, it's a uncomputable problem.
Precisely, that's what you cannot do. You cannot have a Turing machine to know if a Turing machine accepts or not a language. Precisely that is the problem. Suppose you have a Turing machine here, and you want to evaluate if this Turing machine that you can call, let's say that's, what letter is that? I don't know, alpha. You have an alpha Turing machine, and you want to know if this Turing machine is finishes or not. So if you want to say, okay, this machine halted, then you continue the execution of this machine, because you remember, in order to connect to Turing machines, you connect through the halt state, and the halt state is the next initial state. So you halt it, and then if it halts, then you write, then you can halt as well. And let's say it's let's suppose we have something like this. You run this Turing machine, and if it halts, then you want to halt as well. So you don't need to do anything else. And if it doesn't halt, then you also don't need to do anything as well. So you can say, if a machine halts, you halt as well. The problem comes when you want to reverse its behavior, because then you say, okay, the contrary. When this machine does not halt, then you want to halt. Then you would say, okay, this machine didn't halt, then you halt here, you try to see some output here. However, if this machine didn't halt, how can you halt? You don't know, because this machine is still running. So you will never execute what is here in order to change the behavior. So that's why you cannot reverse or you cannot you cannot halt if the machine you are trying to evaluate does not halt, and vice versa. This is why you cannot do a Turing machine that evaluates if the previous Turing machine halted or not. If it halts, it already halted, then you can halt as well. But if you want to reverse to halt if it didn't halt, it's almost obvious that you will not halt as well. You cannot halt if the previous one didn't halt. Why? Because you are evaluating in a sequence like this. In terms of software engineering, suppose you want to evaluate if a certain program that is written in some language will stop or it will get hanged. If it gets hanged, it means it will run forever. Can you know if a certain program will be hanged without executing it? The answer is no, because it depends on a lot of variables and circumstances. Then you cannot do a program evaluator that evaluates if a program will hang or not, because when it runs, it will hang as well. You see, it's exactly the same problem. And if we go back to this part, if we find the complement from L0, then things are much better, because it says W0 such as W0 accepts W. Then it works, because if it accepts it, it stops. Then there is a number that accepts itself, and if it doesn't, L0 prime or L0 complement won't accept it as well. So here we have a very interesting property that L0, there is a machine, L0 is Turing as acceptable. So this complement is acceptable, but the original L0 is not Turing acceptable. Meaning that L0 is Turing acceptable, but because its complement, which is this one, is not Turing acceptable, this is not decidable. Because remember that for a language to be decidable, the language itself and its complement should be acceptable. Because this is acceptable and this is not acceptable, then this is not a decidable language. So L0 complement or L0 prime is not decidable. Is Turing acceptable, but not decidable. And if someone asks you why it's not decidable, well, you know very well, because its complement is not Turing acceptable. That is L0. And of course, if it's not acceptable, it's not decidable. L0 is not Turing acceptable, and of course, not decidable. It's not, you shouldn't ask if it's decidable, if it's not Turing acceptable, because already, you know, it's for sure, if not acceptable, it cannot be decidable. But just I write it so that you remember it, okay? And also, in the previous question, you said something that I took note here of, it's hard. No, to be hard or to be a hard problem or NP complete has not to do with computability. Computability is it's acceptable or not by a Turing machine. If it's acceptable for a Turing machine, it's computable. So let's write it as a table. So a problem, or let's say a language, can be computable or not computable. And computable can be, which in this case is acceptable by Turing machine, or a phrase structured language. All this is exactly the same. And this can be decidable or undecidable. In order to be decidable, then L and its complement are PSL. Undecidable, the complement is not PSL. This is the difference. Okay, now for all computable, decidable or undecidable, so we recap here, we have hard problems and P complete or P problems, which are sometimes called soft problems. But when we talk about this, then we are talking about complexity. From this, we start talking about complexity. So, and NP, or the P and NP, P means it can be solved in polynomial time. Its complexity is polynomial. Polynomial means that if you have certain n, then its complexity will be under a polynomial, which is n cubed plus 2n plus n, maybe plus a constant. So this is a polynomial. However, non-polynomial, you have an n, which the n can be the size of the string, for example, and it's larger than polynomial, meaning that there is a number, a base number, and then this n goes as an exponent. So starting from there, from exponential complexity, you will have problems that are NP, and these problems are called hard. However, both P and NP are computable. The problem with NP is that it can get years to have a solution, millions of years, because when a problem grows exponentially, the complexity for a few items is like, I don't know, minutes. Then you add more items, it doubles to hours, then it doubles to days, it doubles to months, years, and then 1,000 years and million years. And the problem, it's hard because you need to optimize it in order to try to solve it. Some problems can be optimized so that They can be solved in a polynomial time, but most of the time they are just approximated. That's why there are a lot of numerical problems. Most of the deep neural networks solve problems in this way by giving you just an approximation, because solving the original problem is NP complete. So if we have time, we will go to complexity after seeing all these subjects. But for now, this is what you need to know about complexity. And complexity can be spatial or temporal. And it can be also defined in terms of Turing machines. And then it's quite easy. Temporal is how many arcs do I have to jump? This is temporal because you suppose that jumping each arc gives you a certain amount of time, assuming they are executed sequentially. And the spatial complexity has to do with how many cells does it have to travel. If you go for a string and go back and then go again, then you repeat this complexity. For example, in order to copy a string, you need to go, take the symbol, move all the way to the right and put it back. Go back to the left and read the next. Go back to the right and put it back. So you see you are traveling n times because you do this for each one of the cells multiplied by n. So it's n squared because n means how many cells you have to travel. So this is just an example. Just these are quick examples to give you an idea of spatial complexity. And but usually complexity of defined in terms of NP and P is given in time. We assume that space is not so critical because the tape of the Turing machine is infinite, so we don't care about space, theoretical. And however, the time, and also there is a correlation between spatial complexity and time complexity, because we assume that most of the movements we have, the time complexity, most of the steps have to do with some traveling on the tape. So you cannot travel further, you cannot have a higher spatial complexity than a temporal complexity. You see why? Because if you travel 10 blocks to the right, then if you want to travel 12 blocks to the right, you cannot do it in 10 steps. So there is always a limitation of spatial complexity by temporal complexity. Okay, well, sorry, this was the 101 on complexity. Very bad introduction, but you have an idea. And that's why, because the question asked about hard. So hard and not hard, the PNNP has not to do with computable and not computable. This is called computable, acceptable by Turing machines, or this is a phrase structured language. These all are synonyms. Decidable is not synonym of computable, you see, but it's related to computable, and undecidable is related as well. But all this part is computable, and not computable has nothing to do with decidable on undecidable, because, well, it has no use to ask this kind of question if it's already not computable. Okay. Okay, now you are becoming experts in computability and complexity, and that's very good, because these are very difficult subjects usually, but you are grasping them very, very nicely. Okay. So finally, yeah. Yes, please.
If we have a machine of 3 or more states, what is the priority to get the machine number?
Terrible question, because I was thinking about that just before when I was explaining that to you. Yeah, because you say you have this. It's no problem when you have the initial state, the half state, and then, wow, you have S0 and you have S1, and maybe you have something like S go to the right, Y goes to the right, and something like this, right? And finally, yeah, this is a very stupid machine, just what I thought right now. So the question of Camilo is, well, how the hell do I know this is S0 and S1? right? Why not this is S1 and this is S0? I can label them in a different way, and of course it will yield a different number. How do I know which one is 0 or 1? Well, the answer is you don't know. And whenever you face a problem like this, you should be given these levels in order to have a unique representation. Because if you don't have them, then you can label as you want. You know this is initial and halt. Oh, you know this is initial and halt, but you don't know about this one. Maybe the most natural way to do it is, okay, if this is closer to initial state, well, maybe I would say this is S0 and this is S1. I would do that, but well, it's this is not a rule. So I would say if you find something like this, then ask, because it's ambiguous.
Does
And
it really matter?
once you, yeah, yes and no. It
Because-
matters just if there is an exam and they tell you, well, give me the exact number that corresponds to this machine, and they expect a number. Just in that sense matters, yeah. But if we are talking about decidable, computable, or not computable, well, of course it doesn't matter. But I want to give you kind of a standard way of representing machines. So the question is relevant in the sense of, well, if I don't know what to do, then what do I do? And the answer is ask. Sorry for saying obvious things, but I think it's necessary in this context.
And if you raise the first arc, the X1, for example, just one initial S1, S0, and H without that arc.
Also, well, you can, yeah, that's another good question, is should I codify those that go to HUD explicitly or not? Because you have here an implicit Y,
Okay.
and you have an implicit blank space. Here you have an implicit X. And yeah, sorry, this is wrong, it's blank. You have an implicit, no. Okay, sorry for that, sorry. Okay, so you have an implicit X here. You have an, no, also no, an implicit blank space. It's already blank space.
Yeah, we withdraw.
And okay, sorry for that. Okay, again, erase your minds. Let's begin again. You have an implicit blank space here, and that's it. And from this state, you have an implicit Y, an implicit blank. And from this one, you have an implicit X and an implicit blank. So the question here that Camilo didn't ask, but thought of, was should we code this, because this will yield a different machine, right? Well, a different number for the same machine. Then I would say no need to codify. If you know that this is the behavior, and this is wrong again, sorry. Okay, if you have this behavior, and this, then do not code. Yeah, so this is our subtleties that even they are not defined in the Brookshire, and maybe even they are not defined in CIPSER, but if you want to know how to convert these numbers and obtain always a number for a Turing machine, well, you need to know what to do with these conventions. So these are the conventions we take for converting these machines. Well, in the case I ask you in an exam, for example, I will try to give you all you need in order not to have ambiguities. But sometimes I cannot think of everything that could arise, and maybe you do. Then let me know. Professor, I don't know what to do in this case. Well, it should be explicit, right? So that's why I'm telling you all this. But I think most exercises you will encounter in the exam will have only 2 states, so relax. Okay, so there is only one subject that is hindering us from finishing this chapter, and this is the grammars. And this is a very complex subject, and I would rather go to the next chapter, because next chapter is very, very interesting, and grammars are kind of for this one is like too complex. Let me show you. So let's see grammar in 10 minutes. Phrase structure grammars in 10 minutes. Please examine figure 3.16. No, sorry. Do not examine it. Don't go to your books. Let me ask you before you know, before. Wait. Okay, so this is a phrase structure grammar. And the particularities of this grammar, or the particularity of this grammar is that differently to all grammars we have seen before, to the left part, you can have anything. You remember that for the regular grammars and context-free grammars, you had the limitation that at the left side, you could have only a single non-terminal symbol, remember? Now you can have anything. That is why these are also called context-sensitive grammars. That's why the previous ones were context-free, because you replace no matter the context of S. But here you have a context for N. The context for N is if N is surrounded by a Y and an X, then you will write this. If N has the context of a Y and a Z, then you do this. And if N is surrounded by this and this, you write this. So why I don't like too much to go deeper into this kind of grammars, because if I ask you what language does this grammar represent, maybe you can spend several minutes, hours figuring what it does. I don't know, it's kind of maybe too complex for us to handle it like mentally. So in order not to break your heads, that's why we don't go deeper into this, and I will give you the answer. So this is the language for this grammar. The famous XN, YN, ZN. So if this is G, the language for this grammar is this one. And belongs to natural numbers. So you can, I mean, if you, now that you know this, you can try to substitute and try to derive, and you can try to find the tree. I mean, it's not that you cannot, but it's not so explicit, you see? You have here, and then you have some operations that instead of inserting here more X, you have some strange operation here that reverses and adds an X for every N. And I don't know why was this grammar designed so difficult. I think you can find a more clear grammar for this language. I'm sure you can. So try it. Well, and in general, the way these grammars are processed by a Turing machine is having a marker. And also this is not like so obvious way of finding it. Something like this, you start having a sequence of configurations by processing a string. Given a grammar, you start with the marker. You see this marker, this line, and then you move this mark and doing some transformations according to the grammar. Well, so you can, if you are interested in this subject, and I think you will be, you can check section 3.4, and you will have the discussion of all these grammars. But of course, I won't ask you, I will not ask you in the exam explicitly how to process a grammar with a Turing machine. Just please do check that every phrase structure language defined by a phrase structure grammar is a Turing acceptable language, meaning that there is always a Turing machine that can accept this grammar. And here is the demonstration. So check it. And finally, well, and that's it. That's the only part that is lacking. But I really want you to, I want you to or I want to go with you for the next chapter, which I think is very interesting, and we need some time for going there. So for now, just I will leave to you this part of the grammars.